Welcome back to the course on superconductivity. Today we're going to talk about thermal stress and strain. We'll first go over the definitions of thermal stress and strain, then see a case for an isotropic material and for a composite superconducting wire. Thermal strain is the deformation of a material caused by a change in temperature. Thermal stress if the stress caused by the thermal strain when the material is not free to expand or contract. On the picture, we can see that the rails got deformed from their original straight path. This is due to the thermal expansion during warm summers. If we look at the situation schematically, we begin with a straight rail of length L0, and due to the sun heat, the rails get hotter. According to the relations on the right-hand side, we can see that the rail is going to expand of the difference in temperature times a coefficient called thermal expansion coefficient. The final temperature being hotter, the rail is going to expand of a length, delta L. Also, if we constrain the rail so that it doesn't expand, an internal stress proportional to the Young's modulus times the thermal strain we calculated earlier will appear. Taking as an example an isotropic material, considering only plane stress. First, for free boundary conditions, that is, the strains can be non-zero. On the x and y axis we have three components, one being the stress directly applied on the axis considered, here x, the stress caused by the Poisson's effect, and the thermal strain. To add all of them up, we convert the stresses into strain with Young's modulus. Since the system is isotropic, free to expand or contract, and the temperature is even over the surface, the total strain in each direction is equal to the thermal strain. This means that the mechanical strain must be zero. We can see that, for this to be true, the stresses on x and y must be equal to 0, or be equal if the Poisson's ratio is 1. However, according to continuum mechanics, a Poisson's ratio of 1 is theoretically impossible, so they are equal to 0. For the fixed boundary condition, where the strains are equal to 0, we have the same relations. However, here for the fixed boundary to be true, the mechanical strain and the thermal strain must cancel each other. Solving the equations, we get that the stresses must be equal and proportional to the thermal stress. The important thing to remember is that an isotropic free body with no temperature gradients does not experience thermal stress, but will expand due to the strain. We will now see a real case with the NB3SN wires. This wire is made with copper as the matrix and NB3SN, also called niobium tin. These materials have different expansion coefficients, resulting in a significant difference in thermal strain when cooling them from the temperature the wire is made, 1000 K, to the operating temperature, which is 4 K. Since the two materials are bonded together, they have to reach the same length after the change in temperature. This will be the start of our demonstration. First, with the system being static, the forces must be equal, giving the first equation. Remembering the basic equations linking force with stress and stress with strain, we modify the force equation to a strain equation. We can rearrange this equation like this. Geometrically, we can also make a new relation linking the strains if the materials are not bonded together, labeled with the subscript 0, and the ones where they are bonded, labeled R. We use the absolute value, since we only need the norms. We now have two equations with two unknowns, and solve the problem with values on the right. We get a tensile strain for the copper of 0.32% and a compressive stress for the superconductor of 0.58%. Using again the stress-strain relation, we can also find the residual thermal stress with 320 MPa for the copper and 957 MPa for the superconductor. To conclude, by definition, the thermal strain is the deformation caused by a change in temperature. Thermal stress is the stress caused by the thermal strain when a material is not free to expand or contract. These concepts are important because they happen every time the superconducting cables are cooled to their operating temperature and must be taken into consideration while designing an apparatus. Furthermore, even for good designs, thermal stress is bound to appear and must be limited to acceptable values. As a side note in superconductors, temperature gradients can occur for several reasons: quench, bad insulation, bad joints, and can create significant thermal stress. Therefore, designers must look for ways to minimize temperature gradients even in case of failure.